Thanks for tuning in with Recro, everyone. Hi, I am Tarun. I work with the marketing team at Recro. Those who don't know about Recro, Recro is a developer-focused platform where we try to connect talented developers with fast-growing startups like Dunzo, Flipkart, Curefit. Yeah. So that is what we do. Today, the session is about like understanding Java's Project Loom and structured concurrency. So I would tell you a little bit more about Srinivas. Srinivas is a principal software engineer at Veracode. In the past, he has worked with the Java platform team at Oracle for 3 years. He's passionate about like solving scalability challenges, and he has a decade of experience in building successful apps. Yeah. I think I can hand over the session to Srinivas. You can start. Go ahead. Yeah.
So everybody is able to hear me, right? So welcome to this session. So today we are going to. I'll start sharing my screen first, and then we can start it. Okay. So let me start sharing my screen. So you're able to see the project, so the presentation title, right? So to welcome all to this session. So we are, this session is going to mainly focus on Project Loom and structured concurrency. So again, this is a pretty advanced topic because like Project Loom is kind of under construction work in the JDK. So it's expected to be built in JDK 17 or JDK maybe 18 or 19. So currently the builds are available. So its experimental builds are available. So people who wants to play around with this project can actually do it. So I'll be actually demonstrating on the experimental builds to see how this thing works. So let's go to the agenda. And so again, safe harbor statement. This is actually a presentation which is my company is not it's not an endorsement of whatever I'm talking about. It's completely on my own. Okay, so the agenda for this presentation is we'll set up a problem statement like how we are building requests for we are generally building backend services. What are the scalability problems we currently have, and how we do synchronous programming to solve some of the scalability problems. And then we'll see establish the context and the requirement for Project Loom, why people are why the JDK team is spending time to build this, and to see how Project Loom can actually help you in organizing your code so that it becomes scalable as well as maintainable code. So that's most important, right? So when we build products, we build so that you write maintainable code so that you don't rewrite the same stuff again and again. So that's the model in which products makes money. So you should not write a software which needs to rewrite every few years or something. So as you can see, the Duke is there. So this Duke has a lot of threads here. So this is going to be mostly a threading and concurrency based stuff. So mostly I'll be starting with some of the basic construct, assuming that people have certain familiarity of the subject. And so it can be if somebody wants more details of that, we could discuss at the end of the presentation. Or if somebody wants maybe request for slightly easier topics also, we can go and maybe do further presentation later. So yeah, let's start with the Little's law. So as you can see, it's a very simple formula, and Little's law was actually built during theorized during the 1960s, and it actually represents the queuing theory model. So when you can imagine Little's law in the context of a bank, so where as you can see, lambda is the number of incoming people, and then when you go to a bank, you have bank others, so you have a lot of counters there. And each counter will take some amount of time to service the customer. So we can keep it as W. And if you keep lambda as the number of people coming inside, so you can theorize a model in which, let's say somebody wants to build a retail bank. How many counters you typically require for that area, depending on the number of people you can expect. So this is a fairly proven theory, and you have mathematical proofs for this. But this could be applied for a modern backend application or a server application we build. Okay, so as you can see, like from the formula where I explained, lambda can be the number of incoming requests. So let's say and W can be a mean latency in which every request gets serviced. Okay, so and L can be the complete capacity of the system which this could handle this. Okay, so let's say you have like 200 million concurrent requests which is automatically happening. Whether I have the capacity, that L determines. Okay, so if L is 2000, then that's the maximum concurrent users you could support at any point of time. We'll now see how these different values get factored in our day-to-day programming. Okay, so there are various factors affecting. So let's say you take a server that typically servers communicate with HTTPS. You have TCP sessions, and OS there should be some capacity in the OS to create a lot of TCP sessions also. So a modern OS can create millions of TCP connections without any problem. So there is no bottlenecks in the number of TCP connection you need to handle for scalability reasons now. But there are other bottlenecks right now. So the number of threads which a VM can create. Let's say like you are running a Tomcat or a Jetty. When you actually hit a system, you are typically creating a thread. So and that how many number of threads the VM can create, that determines the scalability of the system. Let's say it's going to create only 20 threads, then 20 is the maximum number of custom maybe concurrent requests you could support. So that's something it impacts, and also how much each and every thread is blocking, in the sense like let's say a thread you are getting a request. Typically we build microservices platforms right now, so each service will talk to backend services, like 3-4 backend services in the background, combine everything and then give you the result. So all these IO operations are blocking the current thread, waiting for some operations to be complete, and once the operation is complete, then it combines everything and then it gives you the output. So from the blocking point of time, the thread is blocked, the CPU is completely available for something, but again for you're not using the complete hardware in that perspective. So but again, as in every time when you write more blocking code, the W actually impacts. So the mean latency time for servicing one request will actually increase, and that creates an unresponsiveness. So how do we generally solve this unresponsiveness? We create more resources. We just use AWS or like Kubernetes or whatever the chosen framework we have. We just scale to more resources, but we don't really push to really explore that we are actually using the entire capacity of the current resource we have. So that's one thing. When the actual servlet.do get or do post actually gets hit, what happens is that you create another thread, or you take a thread from a thread pool. Generally, we don't create threads in the modern world. We use something called as executor service. People who are familiar with concurrent programming would have actually used executor service to maintain thread pools. You create the threads, and what you do is like, once the thread is created, you do a step-by-step execution of whatever you need to do. Let's say you need to call a database, or you need to call some extra services. You finish all this stuff, and then once the thread is finished, you supply back the response, and your thread is supplied back to the thread pool or something. So this code is pretty easy to do. Like this is what we do every day, and it's synchronous. It's imperative. It does step-by-step execution. But what happens is that it uses the hardware badly, as I already said. And that is another request which has already been there. At the time the thread is blocked, and you are actually blocking some amount of CPU computation, and you are just wasting the time actually. So you're not doing anything useful in that. So and your capacity of your actual machine, which is governed by the Little's law, actually decreases because you're blocking a lot of stuff. So and then what happens is that this leads to bad performance actually. So that's the problem of request per thread model, and people solve it in different ways actually. So one other thing everybody does is that we go to an asynchronous and a non-blocking model. So I don't want to go into specifics of every framework how it works. Node.js works in a certain way. Reactive programming works in a separate way, but everything has the same context or a concept behind, in which you define a list of tasks in form of steps, and each steps execute in a different point of time in different threads. So you don't wait for the specific sequence of code to finish before you move something. You say this is my step, and this is my second step, this is my third step. You configure that, execute in different points of time, and you move to the second request. So rather than actually blocking. So that's the way asynchronous frameworks are very famous. They give you cheap scaling. And one of the important reasons even Node.js got built, because Ryan Dahl, for context, Ryan Dahl is the inventor of Node.js. He went and ran a performance benchmark in Tomcat and was so pissed off, he created Node.js because that is completely async. So this is good for the hardware, but the point is it becomes hard to maintain code and hard to reason code and hard to profile it. And the most important concept here, we have built a lot of abstraction in our imperative programming, built over years, and that is thrown out of the window. And we'll see step by step how this effective abstractions and all this intuition, what as normal imperative programmers have built, is being thrown out, and then for scalability reasons, okay, but that's required. And then we'll set the context for why Project Loom and structured concurrency are required. So next goes to a simple problem. Okay, so we'll start with a very simple code. Okay, so as you can see, it's a very simple code. It takes an input value, which is the value, and I'm trying to place a deposit right now, and I have 3 operations in that. One, I need to compute the exchange rate, and the other one, I need to see the current current interest rates in the market, and then I need to compute all the charges, and I have to give you the result. And let's imagine that this the currency computation and federal fund rates are all external services, okay, just for a thing, and you're gonna block it. So till I get my response from my currency converter, I need to wait, and I need to then make a request for the federal funds rate, and I need to do subtraction of charges. Okay, so this is the way we do. And let's say we place this code in some server side place, and you have, just imagine that you have another you have placed this code in a Spring Boot or any of your chosen framework. So what it does, it creates a thread, and it does a step by step operations, finishes it, and then it goes. So that's how we do here. Okay, let's try to run it. I'm going to give you samples also. So are you, I think you are able to see the screen, I guess. So if some issues, please ping me, like, yeah. Okay, so I'm hoping that you are able to see my my IDE. So let's go this structured. Let's see, I have the structured way. Okay, imperative and blocking. So that's one. So this is a very simple code, and if I run this code, it will so simple, like, yeah, it runs in a sequential way. As you can see, everything runs in a sequential way, and finally I'm getting my result as 69.3. I've put $100. My exchange rate is around 0.7, and my interest rate is minus right now. That's how the world works right now in anywhere around the world. So there is negative interest rates. So, and I get some $69.3. So that's my deposit after some time or something. So we are not don't want to complicate this code, but just want to drive home the point that you are doing an operation step by step. But let's see how we could parallelize this. So yeah, again, I'm hoping that you're able to see the code. And so a non-blocking code, what we can do, we can take a method called compute, and we can say an operation with the same compute method. We could do with adding a by consumer, and make sure that every step of the value, like let's say you compute first stage of the value, is being passed to a second stage. And then let's imagine a proper framework can actually implement all these levels in parallel in its own thread. So you have std value once. If it's the first thing is compute is passed, then you pass it to the second value. Second compute. If second compute is passed, you pass it to the third value, and everything is finished, you publish to a random queue. And this random queue can be a publisher, subscriber, whatever the frameworks. Because we don't need to really go into the implementation of frameworks, because mostly everybody follows some model of actually publishing the results. It can be a queue, it can be some publisher subscriber pattern, or it can be something else. Okay, so so that's the way it does. So it's kind of, you can see. It's become very complicated, but it's fast. This one is fast because once I enter this compute this line of code, and everything is getting executed, my main thread gets out, my service will be really fast actually. So that's one of the important thing we have done here. Okay, so that's, yeah. And let's go to again detour a concept of monads. So monadic functions are like superpowers. Okay, so actually what you saw initially is a normal function. We can define a normal function as like takes an input, does some value, gives you a result, but if there is a problem, you'll get an exception. Okay, that's how a normal function works. A monadic function actually gives superpower. So what happens, right? You take a value, you wrap into a composer context, and once the composer is finished with this value, finished with this processing, it actually wraps the output to another, wraps the output to a monadic function, and then it returns you back. I'll give you an example which people can relate it. So if somebody has worked in Java 8+, you would have seen this flat map feature. An optional.flat map is also added, and there is completable that you then compose model. So what it takes an input, wraps it with applies the mapper on that, and takes the output and then wraps it back. So that's how a monadic function works. Okay, so we'll write another tamed code that was so complex. Actually, we could write it more simpler here. And what we can do is that we could put the compute method in the you could actually make everything as a completable future. So for a detour, completable future, I just want to explain is that it takes an async function and it executes in a separate thread. Okay, it's a completely non-blocking way of actually writing code. And I don't want to get into the very complex part of how completable future works. So if that's required, maybe you could do it in another session. Okay, so you can just imagine that completable future takes a function and it execute in a separate thread. It's not going to execute in your main thread. That's the important thing. So everything you can imagine like this, everything is supplied as an async. So what you can do, you can say the same concept. We have composed the value. So each and every value, if this stage is correct, then the output of the value gets to the second stage. If the output of the value, if this stage is correct, and output of the values goes to this stage, and everything is complete, you can again say a logger.log error if something goes wrong in the middle, and also exception also get propagated. And you can say if everything is correct, again you publish to a random place. Maybe you have your choicest reactive frameworks, or like you publish to queue. So that's how you do. Let's write even let's try to run this code actually. So I've already ran this code, and I've actually placed another timeout here because everything is going to run in parallel, and without timeout the main thread will get exited immediately. So if you can do it again, does the same thing. It waits for a few seconds because I've had the timeout, and then it is done. But the important part is every stage of this executes in a different time, and this code will scale. This code will scale exponentially compared to what you have in your original blocking code. That's one of the things. But again, it's very complex, and again you have lost an important ability to return values. So again, returning values is very important in the sense like once you are able to return a value, it's far easier to test the code. And let's say, how do you test this code? You have to run maybe a Mockito framework or something, and then say whether this method, some people have experience with Mockito frameworks could relate here. So you have to run a Mockito framework, and then maybe you can say this method is called somewhere with the correct value or something. So that's the only way to test the code. But the original code is far easier to test in the sense like I could test it with the correct input and output, and I could say, oh, this thing works. So, but once you are having this composition and a sync way of doing, one of the things you lose is the testability of the code. Okay, let's say we could try to improve this. This again becomes even more harmful. Let's say if you want to return this code. Okay, so as I said, monads have an ability to apply a mapper function, which is completely what we are doing here. We are doing a lot of mapping functions here. Take the value, map to another compute, and finally, when everything is done, we could wrap the actual value and return it back. Okay, so this can be done. This can completely work. So the problem with having this type of thing is, right, you're going to pollute the entire call stack. So the entire call stack from, let's say, servlet.doGet or doPost is going to be completely filled with completable future, and you cannot maintain this code. So that's the problem of purely going async way. So this either you have to handle with random places, you're publishing, subscribing, you are dealing with callback health, or you're going to actually make your pollute your entire call stack with monads. So that's the problem we have finally ended up into. So let's go again, rewind some decades and look at a concept of structured programming, which again we are born with structured programming. We can't relate to how a pre-structured programming really worked. Okay, so let's go into this actually. So structured programming gives you a tenant in which any branching of the code has to come back to the original place. So you write a if else code. Once there is an if, there will be an else, and the control flow comes back to the main, and then it goes to an exit. So that's how it follows. It goes a sequential manner in which step by execution, and then it goes to the named exit. And also any branch function, any branching function should return back the control to it. So you call a function. When you call a function, it has to do either a value, it has to return a value, or it has to do some operations, and it has to throw an exception. So all these three functions are only allowed because the control flow should come back to the main. So this is how we do structured. This is how we have been brought up with, and also this very important thing to relate in the sense like before this was invented, people are using GOTO statements actually. So we would have maybe studied in our undergrad or something. GOTO is very harmful, but again we'll see how GOTO is becoming more harmful right now in the modern programming. Okay, so again, Dijkstra's actually structured programming was invented by Dijkstra. You might have seen a lot of graphs algorithms be named after him. He's a brilliant computer scientist. A lot of algorithms have been, and most important contribution of his is structured programming. So Dijkstra's main concern was abstraction. So we want to write programs that you can. It's not too big to hold in your head at all at once. So when you see the first program. This is easier to hold in your head, but this might not be so easier to hold in your head. But this scales and that doesn't scale. That's a different part. So what his pattern was, like we need to write smaller subroutines, and the smaller subroutines should be completely held as a black box. So typically when we write system.out println, we don't give a damn about how it's implemented. What we expect is that we have whatever we are supplying the text value inside system.out println prints and gets you back the control. It doesn't say that I'm gonna print and then send you a message to somewhere else and you listen to that place to actually say whether I printed or not. So that's the problem with the sync programming. So it's also, there is two types of scalability. One is the actual code scalability. The other one is the actual writing and the code scalability and execution scalability. Like it has to scale through execution, take up the least resources, and it has to scale for a lot of customers. That's one thing. The other one is maintenance scalability. So if you write a lot of code, maybe these things might not scale in that context. In essentially, I could get this one function correctly, maybe a few functions correctly. But if I want to write this type of programming, my entire code base, then you will end up looking at some Node.js project. Okay, so that's why like people start with funny stuffs, and then maybe after a few years, when they really make some money out of their product, they really write Java code and make it stable and other stuff. That's how even been my experience of how startups mature to write very stable code actually. So, and when one deviates from the sequence code, then as I mentioned, it becomes hard to reason. So again, if you look at the unstructured programming, that is in the towards the left of the 1960s, where you use GOTO labels, and from GOTO labels you go to different places, and finally the code can finish. The modern GOTO statements are this completable feature that run async. And whenever you say execute a service that submit any async function when you do, or you write, you use a reactive framework to publish to different places, publisher subscriber patterns that when you use. And also when you use like Golang, which is actually built a Go keyword into it, like a GOTO label. Okay, so like it's the modern GOTO right now. So what again is the thesis is that you can write proper, you can reason the code, definitely you can write a lot of workable code, and that was the statement. That was the statement which was given to even in 1960s, where GOTO labels were actually said, oh, it's just Donald Knuth actually argued in the sense like you would have again heard about the scientist Donald Knuth. A lot of algorithms have been written by him, and Donald Knuth actually argued that you can actually just write. You just need to be reasoning the GOTO statements correctly to write in proper code. So typically, you can write async programming. It's not that it cannot be written, but in the sense like you need to be an expert, or like it works properly and it doesn't scale in the sense like when you write a lot and lots of code, it doesn't scale well from the maintenance perspective. So what structured concurrency in the sense thesis says in that sense, like when you have a thread, let's say a main thread, you can create a number of parallel tasks. And whatever you do, you have to join those parallel tasks before you go to the next problem. Let's say the same function, it can have multiple parallel tasks running, but make sure you join all the parallel tasks before you exit. So to achieve this, so the whole point of this join is to make sure that you get rid of GOTO statements. You have a control flow statement in the sense like I'm branching out, but I am actually making sure that I'm joining back everything before I go to the next problem. So that is one of the important things. So what it gives you finally, right? It gives you subroutine certainty. So typically you can go back and write a program like what we wrote in the first line of code, step by step. Each can execute in different threads, and you can actually ensure the subroutine gives you a stable output. If there is a problem, it can give you a error. So that's one of the things. Subroutine safety should be a thing. And the other one is automatic resource cleanups. So automatic resource cleanups is nothing but once I've used all these threads, I should be in a position to destroy all these threads and go. And this should make testing easy. And also the abstractions which we have built so long that we have been discussing, that any control flow has to merge, any function has to take an input and returns an exception or returns a value. So that is a construct we have been building over a long periods of time. That should be open. It should not be saying like system.out.println, okay, I'm going to publish to another queue, or like in a publisher subscriber, you listen to that subscriber to actually figure out whether I printed my line or something. So that should not be the case. So, and that's the aim of structured concurrency. And we have established the problem, and we have said structured concurrency will solve this problem, but how JDK is going to solve it is going to be the next part of the presentation. So to achieve structured concurrency, there are some prerequisites where the JDK has to be performing well. So first thing is that your creation of threads should be cheap. But currently in our JDK, creation of threads is not cheap. That's why we create a lot of executor services where we actually pool our threads instead of actually creating new threads. So if any modern programming who has done multi-concurrency programming will never go and create thread.new thread. So typically they will create an executor service, use the executor service as a means of creation of thread in front. And then once the threads are created, you actually subscribe to take one of the threads, execute your service, and give it back. So that's what we do. So I'll go to the presentation again. Sorry. So that's how we do. And so the prerequisite for it is for me to create and destroy threads cheaply, and we should not consume a lot of memory. And there should be a language construct in which to organize this. So that's the three things Project Loom and structured concurrency is focusing. Let's go to Project Loom. Before we go to the actual constructs of Project Loom, we'll go to a throwback of what a thread is really. So Java.lang thread is being built still from Java 1. It's a 25-year-old idea. And one of the most important concept of thread, it always maps to an OS thread. So whenever you create a thread, it always maps to a kernel thread. It's not that it's going to be something within the JVM. It has an OS connection to it. And also OS threads are completely build generic. So it's not like only used for IO or like only for compute and other stuff, because a variety of applications runs in an OS, and it can actually have threads which are generically designed. So an OS memory actually can grow, but it cannot shrink. That's one of the problems. And generally threads can go up to megabytes of memory. So that's why we use an executor to actually make it more efficient. So let's go to virtual threads. Okay. So virtual threads is the new construct which the Project Loom has built. They are completely lightweight, and virtual threads are completely handled within the VM. So there is no connection to the OS, and they are scheduled and multiplexed on a carrier thread. So the carrier thread is the actual kernel thread which is going to be used, but the virtual threads are completely within the VM itself. So it can be suspended and resumed, and you can create millions of threads. So one of the problem statement we said that we should be able to create and destroy threads cheaply, and that's the way you can scale. Otherwise, you can't scale in this world. So let's go to some code actually. So we'll see. Maybe I'll go to the continuation part, and before I touch the code actually. Okay. So the unit of the virtual thread, what Project Loom is designed, is known as a continuation. Again, continuation, as you can see, takes a scope, and it can yield. It can, so which means it can stop, it can yield control, and it can run again. Let's see it actually how it works in the real world. So as you see this code, you have a scope called continuation scope, and the continuations will take this scope and it will actually run. We can run any code within this actually. So if we start running this code, let's see how it runs. So as you see, it says before, okay, it says before, and what happens at the line number 11, when you say yield, it gives back the control. So when I say, then I'm checking whether it's done. So the continuation is not done at the line 15, and line 16, I'm calling the continuation again to run. So it doesn't start from line number 10, it starts from line number 12 because it has yielded from here, and it starts again from here. So what do you have in the sense, like you are able to block the stack, store the stack somewhere else in the VM. I don't want to really go into the implementation details how it's done in the VM, but you can just imagine that it acts like a thread where it could yield control, and then it could save the context somewhere. And then once you need to run the context again, you can again call the continuation.run, and you could actually start the continuation. So that is the base. This will actually replace a thread inside it. Okay, so let's go back to the presentation. And what will be a virtual thread is nothing but a continuation and a scheduler. As I said, instead of actually using a proper virtual kernel thread, a virtual thread actually uses a continuation, and it uses a carrier thread actually. So this carrier scheduler, this executor scheduler, is nothing but contains a carrier thread, which is actually a kernel thread, and you are multiplexing a lot of threads into the carrier thread. So you can create millions of continuations within millions of continuations and virtual threads, and it could be multiplexed in a single thread. So you don't need to worry about my memory is going to get over if I'm going to create a lot of threads. So that's something important. Let's go back to some code actually. So let's try to write structured concurrency now. So as you can see, let's start with the unstructured concurrency. So yeah, okay. So yeah. Before I want to, so generally with this is the way we write. We see again, you're branching out from task 1, and then your structure is ended, okay, and then you're branching out to task 2, and only when you call shut down your entire executor, then it comes back and closes all the tasks and finishes it. So this is an example of a non-structured concurrency. And let's go to a structured concurrency example, and I'll explain the project loop constructs while I explain my structured concurrency code. So as you can see, so there is another thread pool executor called virtual thread pool executor, and this virtual thread pools can create any number of threads. Okay, so when you look at the executor service, you have like cache thread pools, you have fixed thread pools which you used before, and there is another method which has been added called as a virtual thread pool executor. So virtual thread pools can create any number of threads, and the creation of threads is very cheap. Generally, what you do when you create a new fixed thread pool, you don't generally create within a method because it's kind of expensive. You create within a bean or something where people are familiar with Spring applications. You create it in a bean, and then you inject the bean so that you share the same resource everywhere. But creation of virtual threads are so cheap, you can actually create it within a method, and then you can close it. And I'll explain you how we can close it actually. So let's run this code. So when you run this code, both, as you can see, these two tasks have been executed in parallel because both are executor services. You are actually submitting this async workflow in some other thread. Both run in different threads, but everything at the line number 51, all this thing joins together automatically. And in the line number 52, you can see that structure is ended. So as you can see, this code you cannot execute maybe in Java 15 or something before actually. This execute only the Project Loom build, because what executor implements right now is an auto-closable. Somebody who have implemented more than Java 7 plus code, we regularly use for files actually, so that you automatically close the, instead of using try catch finally, what we do is we use try with resources. Try with resources actually closes the resource before you do. The same way, when you open this resource, like it's also typically a resource, a virtual thread pool, you actually execute something, and when you exit this block, you have joined everything, closed it, killed the thread, and then you proceed further. So that's way you are what I've mentioned in my old flow. Let me get back to this presentation. Okay, so in my old flow, what I have said, I've been able to create some parallel tasks, and all these tasks should be created cheaply, which the way we are creating via virtual threads, and we are able to join within the construct of the code before we proceed. So we are having a structured way of organizing our concurrency, and we are able to scale by able to creating any number of threads without any problems in that. So that's one thing. Maybe I'll give you another example which completable features use. Again, completable features are easy ways to actually write the sync code. Try to run that. Okay. So if we run, I'll just explain the code before we run it. So what I do is like I want to create like 10 or 10 async tasks. So you can just imagine run async will create another async pool, run another system.println in a separate thread. Okay, so you are supplying a thread pool here, and again we are using a virtual thread pool here. We are actually supplying this virtual thread pool inside the structured concurrency block. And what we do is, right, we are able to, we are able to actually we are able to create some number of tasks, and we are able to, we are actually printing out everything in parallel. So that's what we are going to do. Let's see how this works. And this could be replaced with any one of your important code also. Everything can be done in parallel. So as you can see, everything is out of order execution. Everything is executed in different threads, and you are actually starting the branching here, and you are ending the branching here. So you have structured concurrency. You're able to create threads very cheaply, and you are able to destroy threads also very cheaply. And that's the way we this thing works. So let's go back to the presentation for some time, and again, I just want to explain some of the concepts of locks actually. So typically we use locks, and also like if somebody who worked in Java concurrent API, that will be called reentrant locks. And how this locks works also, right? Typically when we use virtual threads, the same locking mechanism, everything will work. Even like a normal thread, you can actually lock a state, and then so that you concurrently update only the logical parts of it rather than you having race conditions in that. I'll give you an example for that. But typically what it does, right, there is a change in the lock support.park. So when you run any concurrent reentrant lock, if you look at the call stackers, you will get into this method. So what it does is that it checks if it's a virtual thread. If it's a virtual thread, then it parks the virtual thread. If it's a normal thread, then it will park the kernel thread. That's how it works. Okay, so let's see how this locks also works. So as you can see, again, I'm using a virtual thread pool here with the deadline. And again, I just want to explain something about the deadline actually, which I can explain before. Let's say one of the submitter executor task you submitted is rogue, and then let's say it's calling a API which is not responding. So what you can do is that you can set the deadline as 10 seconds. If any one of this task is taking more than 10 seconds, then it cancels the entire task. So that cancels the entire thing and then throws you an exception. That's one of the things which automatically it does. So that's why we say we give you a deadline here. So and let's look at the lock example. And if you look at here, I'm having a shared state here, which is a field variable, and I'm going to update this stack state in a logical way. So I lock it here, and then I update with my task one, and I'm sprinting, and I'm going to update the second lock with properly doing a proper locking here. So just want to demonstrate here. So current status is right now task 2, because the last update I did was task 2. Both were doing in separate threads, but I'm able to achieve the concurrency of the locks, that is shared state concurrency, in the sense like I'm not having a race condition in that, and I'm able to update the shared state properly. That's one of the things we need to drive home here. So again, we are doing the same problem. This is what I already explained, and we'll actually look at the place deposit method, how we can write the initial method which we did. How did we write in the imperative blocking way, which we did was to compute one, compute again, compute the third time, and then you accumulate the results and then you get it back. So that's something we did in the initial code. So let's see how we are doing this in the structured concurrency world. So with Project Loom. Okay, so let me do this, the same code. I'll explain the code before I run. If you look at here, again, we are creating a virtual thread pool here with a deadline. And what you do is that, again, we are supplying asyncs. But what this ensure in the sense, like we are able to join the code, destroy the thread pools, create threads in the way I'm going to get the same result. I'm getting the same result, but everything has been executed in a different thread. You're not blocking the main thread. You're not blocking any main thread resources. That's one of the things which this can do. So what we have done here is like we have scaled up the system. We have made sure that we are writing in a proper way so that it's not very confusing. And also the most important thing is, right, this again looks like a normal method. So it takes a value. It's not returning some fancy monadic values. It takes a value, does the computation parts, finishes it, joins it. If there is an exception, I'm going to get an exception. If the value is completed, then I'm going to get the correct value of it. So you are going to write a proper subroutine with all the safety of your structured programming, but you're going to scale it in a larger way. That's what Project Structured Concurrency does. Let me go back to the presentation again. Okay. Again, we have already established in the way how we are doing structured concurrency, like how we are exploiting the structure within the code and executing everything in a different thread, and how we are accumulating, and we are actually achieving a proper scalability with writing proper maintainable code, which can last for 5 to 10 years. That's important thing, because if we rewrite our same product every few years, you are wasting a lot of money in that. So we have to maintain, we have to write a code set today, so it's going to stay for the next 10 years without any change. So that's one of the things, one of the output of actually writing a proper product that makes money actually in the long run. Okay, so exploiting parallelism. So as you can see, with this hapless code which we have written, it's a very simple code. Any college student and any high school student can write. So what you can do, we are going to sum up 100 numbers. Okay, so what you do, you initialize a sum variable here, and you can say sum equal to sum plus I. So what I am accumulating is that the sum variable accumulates every value, and finally it returns a sum. And the same thing, if you have Java 8 plus, people could easily understand this. So there is an in-stream class in Java 8 where you can say range.0 to 100, and you can parallel, you can say dot parallel and sum. But the whole point I want to drive is this works in a two different ways actually. So the first one on the left is called as an accumulator pattern. The second one is a divide and conquer pattern. Let's see how the accumulator pattern works. So accumulator pattern works like step by step. Each and every time I take 1, then I will add 2, then I will get 3, then I will add 3 and I'll get 6. So you get the sum. So the problem with this model, you can never parallelize this. So let's say I have a 100 core machine. It doesn't parallelize because it can only scale up to only one core. That's what the single core. If you have a faster single core, if you have 100 cores in your brand new machine, you cannot scale this code at all. So that's the problem with accumulator pattern. Because what's the problem in our structured programming in the sense, we generally follows an accumulator pattern in the sense, in the old code which we require data flow dependency was there. We need to do step-by-step execution to do it. But in this, what's the point I'm driving home here is that every problem doesn't require that. So you have to look at the problem whether it really requires that. If it really requires, use structured concurrency, use everything, do everything in parallel, and then accumulate the value and then send it back. But if you don't want it, you can do it in a different way. So divide and conquer. So if I do the same problem in this code, like the right side code executes in a very different way. So left side code executes in this way, which is very linear. It cannot scale. But the right side of the code, whatever we discussed, execute everything in parallel. So every computation here, 3 plus 4 or 1 plus 2, 5 plus 2 or 7 plus 8, everything can be executed in parallel. Because I don't give a damn if 1 plus 2 is executed and 19 plus 100 is executed. Both are orthogonal, separate problems. So if you are able to decompose my problem separately, without interdependency, without data flow dependency, I could scale to a very different level. So that's what we'll see in the next part of the code. So this is a very common use case actually, because let's say I'm building a product where I crawl the web actually. So I'm going to download. Let's see, you imagine you're working in Google also. You're going to crawl the entire world. Okay, so you are going to crawl a lot of websites, and you're going to take values in it, And in our use cases, we have to find some patterns in which whether some security issues are there. As I work in a security engineering company, we will generally look for some security. Let's say some CD is published somewhere, and we have to do a lot of analysis over crawling a lot of URLs. So what we can do is that we can do everything in parallel because two URLs can be separately downloaded. These are independent subproblems. So as you can see, CS 101, if you have divide and conquer programming, you can have independent subproblems. If the two subproblems doesn't depend on each other, it can scale logarithmically. So that's important. So let's look at the code also here. So download parallel. Let's go download parallel code. So we're able to see this code, right? So here I have defined I'm just defining two websites here, CNN or Google.com. Again, I'm creating a virtual thread executor with a deadline, maybe 100 seconds is the max anything could take. And I'm creating an HTTP client builder. So Java 11 plus people who have used Java 11 plus would have seen this brand new API which has already built, is released. It is way better than Apache HTTP client or whatever is outside, and it could do easier actually. So let's drive on the point actually. So again, I'm passing this executor service to a try release method where I'm going to create number of tasks. So I'm going to iterate each and every URLs, and each and every URL is going to give you a sync. It's going to send you a separate asynchronous request. So what I'm going to do, everything I'm going to download in parallel, and I'm going to just print it out. So that's the aim of this code. And handling this response here, I'm just picking up the body. You can do complicated analysis also, and all this handling can be done in parallel. Before if you sequentially do it, it will take millions of years maybe if you want to crawl the entire world. So now I have done I've crawled both these URLs parallelly, and I have downloaded the content of the text inside this URL. So you are actually supplying all this in its own thread pool, downloading everything. You are actually finishing out the execution part, and you are going to return the value. Right here, I'm just printing it out. You can also return this value somewhere else in the code. So exploit parallelism where is there, and make sure that you are able to decompose problems into a divide and conquer, because linear scalability and logarithmic scalability are two different things if n is very high. So when n is too much high, let's say n equal to 10, anybody could code. If n equal to a million, then you need thinking to code actually. So that separates the men from the boys. Oh, so that's I want to drive home the point. And I just want to say some of the limitations right now in virtual threads. You can't use a synchronous block. So before we would have seen this code, right now everything is in reentrant block. As you see, this is a reentrant block code. Anybody who would have built Java concurrency APIs, you would know about something about reentrant block. But I think the support will be there for synchronous block also in the future. And continuations doesn't work with native code actually. So you have some JNI code. This doesn't work right now because native fronts work completely differently. And then Java.util.concurrent libraries require some retuning in the sense that we need Java.concurrent was written in the sense that threads were not really cheap resources. But right now threads are cheap resources. So there is a retuning required to actually implement that. So as you can see, these are the references. There is OpenJDK code there, and you can look at the code, and there are builds available. And this is a build I directly downloaded from the internet. It completely works without any issues. You can use the IntelliJ to actually run this, experiment how structured concurrency works. And let me go back to my presentation. Yeah, and you can look at the Project Loom presentations which are already available. And that's my presentation. I'm done with my PPT, and let's go to let's open the code for discussions.
Srinivasan, thanks for the amazing session. Yeah, I think I would like to know how was the session in the comment section. Everyone once at least. Yeah. And you can go ahead, if anyone have the questions, you can try to add in the questions tab. Yeah. Srinivasan, someone has posted a question. Yeah. in the chat window, but yeah.
Yeah, I'm looking at that actually. So one other thing is, right, parallel stream, as I mentioned even before, parallel stream is actually used for actually compute bound tasks. But for virtual threads, the most important use case for virtual threads are IO bound tasks. Let's say you are the example which I showed, where I actually download from multiple websites or something like that. I want to write a crawler which wants to download from millions of websites. So it should always be used for IO bound stuff. When you look at a parallel stream, right? When you parallel stream, when you look deeply into the code, it will use something something called as a fork-join common pool. And fork-join common pool actually uses only the number of CPU counts as the thread pool size. Let's say you have an 8-core CPU, you are going to only get 8 threads in that. So if you have a compute bound task, then you should go for parallel stream. The example which I showed there, where you want to compute a sum of 100 numbers, you can use a parallel stream for that. That is a use case for that. But let's say you want to download a millions website, that's not the place where you use parallel streams.
Yeah, Anirudh, does it answer your questions? Anyone have any more questions? Srinivas, there is one more question from Pojit. Yeah. Srinivas, can you hear me?
Yeah, I'm able to hear you. I'm looking at the question.
Yeah,
so, on an unrelated note, I'll just read the question so that everybody could even, it will be easier for people to relate actually. So Saurav actually said, like, on an unrelated note, where does Node.js start failing short of the requirement since it uses the async methods too? Suppose if I don't have the compute heavy task. Okay, so one other thing is that Node.js actually scales well. It does everything what JDK does, even though it does even better. But the problem where it doesn't scale in the sense if you have lots and lots of code and you're doing actual production running, you are actually serving customers. Okay, so there is a two different thing. When a product doesn't have a customer, then there's a different problem. But when you have real customers for that, then you will be at the real table. And if you start debugging problems in your code, and there is multiple, like 100 people are actually contributing to your code base, then it becomes a very messy code. So that's one of the problems. It generally scales very nicely. And one of the inspirations for actually writing Node.js was Tomcat, because it was so underperforming. So that's the JDK. So the first benefits of what you see with Project Loom will be seen in areas like Tomcat and JT, where that will be able to create millions of threads for you. So you don't need to write all this complicated structured concurrency code. So what it does is, right, you just take the latest version of your JT, maybe once after Project Loom is released, you will see magnitudes of performance increase, because internally it will be start using virtual threads rather than actually normal threads. So that's how it will start. And then you could do proper async program, like whatever I explained. If you want to really reduce the M value, I'll do another. I'll just go to my presentation back, and I want to tell you something here. So if you look at again to the base problem formula we are seeing. So here, if you want to really work on the W value, right? Sorry, if you want to really work on the W, which is the mean latency part, then you require all this parallel stuff, all this structured concurrency in which organizing your parallel code actually. But if you don't, in general, if you just want to write simple code, simple structured programming, if you download the latest Tomcat JT after JDK with Loom is released, you will give magnitudes of performance increase. You don't need to do anything about that. Yes, so Aniruddha Pawar has said, just to be more confident, is it real that I could create as many threads as I want in a new virtual thread pool executor, irrespective of the heap size? So the answer is yes. The point is, right, virtual thread pools are created in the sense creation and deletion of threads are so cheap, you could do any number of threads. So one kernel thread, which is the new thread which you're creating right now, can be multiplexed with around like 100,000 virtual threads. So you can see, let's say if your CPU supports around 2,000 threads, then you have millions of threads you can actually create and destroy. And also the whole point is, right, the destruction of threads is also cheaper, right? So you can create and then destroy it as soon as possible, so that you can improve your performance multitude times. So that's one of the important thing. And also when you actually use the virtual threads, everything lies within the VM itself. So it's very complicated code how continuations work, which I don't want to get into it right now. But continuations make sure that you don't you can create as many number of threads without actually breaking your memory. It doesn't, again, I'm saying it doesn't replace anything. The normal thread t equal to new thread, if you do it, you will. So again, I will just read out the question for Maheshwaran. As said, I'm not really good at threads, but how does a virtual threads perform over a normal thread? It doesn't replace a normal thread for code development. No. So normal thread actually is there. It will be still there. So normal thread, when you create, you have to create so that you do some real CPU bound operations. Let's say you're do parallel compute. At that point, you can create a normal thread using parallel streams. When you internally call parallel stream internally, it has a fork join common pool where it actually creates real threads and you do real computational problem and then solve it. But when you create virtual threads, the IO bound task where you just need to wait for some service to give you a response, where you don't need to do anything. Your CPU is completely, you don't need to block your CPU. You just need the stack to get blocked, where till it waits to actually gets the output. Yeah. Okay, I understood both the parallel stream uses fork join strategy, but it's just parallel stream uses OS threads under the hood, and hence the pool size is limited, and thread count, is that correct? Yes. So the points in parallel stream uses the thread within your with which you real kernel threads, and also anyway, whenever you're doing compute bound task, you should never create anything more than your core size. So let's say your CPU is 8-core task. Eight threads is enough to do whatever compute bound task. If you want to some maybe 1,000 in parallel, it's going to be only 8 threads. But if you want to do IO bound task, then you can create lots of threads. Before in the world, we are creating normal threads to do this. But what in the new virtual thread platform, you can create virtual threads to do it. That's the Project Loom is trying to address.
Srinivasan, we have missed one question by Pujit. Is there any company or product that is currently using Project Loom?
No, only Srinivasan Raghavan is using. And the developers who are using. So currently currently this Project Loom is in incubation phase, and right now, but you can actually download the builds. It is not for production ready. It's advisable not to run any production code in that, but you can definitely build like experimental features in that, so that when things get ready, you can directly port into production. So that's the way it's been working right now, and you can experiment with the build actually. So it's again built on JDK 17. Actually, you can use all the features which are already available prior till Java 16.
Yep. Anyone have any more questions?
No. Again, so the next question is, could we say this implementation in Java would be very similar to what in Golang does? So Golang actually implements GOTO programming. Okay, so that's what my thesis initially presented. When you do Go function, it is actually a GOTO statement. You are going to somewhere and then you are not returning by the control flow. Yes, there are channels. There is something called as Go channels or something where you can maintain this work. Again, as I said, you can write very complicated concurrent code, asynchronous code. This could be maintained, but the problem is whether you could write it easily and whether you could maintain that code for 10 years or something, where you need to really focus on your business logic rather than actually writing fancy asynchronous code. That's the thesis in which this presentation is done. So in certain case, Golang via virtual threads is analogous to Golang in the sense like we are creating VM based threads. Golang also creates very lightweight threads instead of actually creating kernel threads. In a way that we are creating Go functions, but what we are doing is we are in JDK. What it does is that it organizes in a proper way so that you use it in the right context rather than spraying around Go functions everywhere.
Any more questions?
What would you suggest? Should we wait for the stable release, or we could start using builds on the go? That's completely depends on whatever the product you're building right now. If you are in a Java environment, it is you could do experimentally. You can have this code, and once the release is done, you could actually move to this build. And if you're going to go programming, you can write go function and deal with the complexity later. That's also deal with the complexity. Maybe 5 years down the line, your code might be unreadable, and you will some other down the line engineer will actually make some choicest statements of whoever has written the code today, and you will use all the parliamentary languages who has written this code, and then he will start writing in Project Loom. And that's how the things work in the world. So when startup actually generally comes, whatever their main function is to actually get the code out. You can see the evolution of Twitter also. So Twitter was initially written on Ruby on Rails, and actually then they recoded everything in JVM platform. They used Groovy, Scala, and Kotlin maybe, but again they used JVM platform to do it. And that's how mature teams actually move again to write code so that you can maintain for 5 years or 10 years. You will, because startups, you need to actually build a product, get it out, get users into it. So if you want to write a code for 10 years, you might have the technology, but your startup would have folded by the first year itself. So everything works on different contexts of which stage the company is working on. So if I pretty much my Veracode software composition analysis, let's say imagine it's going to stay for the next 10 years, I should be coding in JVM platform so that I write maintainable code. So that in 10 years down the line, somebody could take a dusty jar and put in the latest JVM. Everything works, scales. You use the same code right now, use the latest version of JT, and your code will scale. You don't need to do anything even fancy. So that's what for the question even before, right? Should you do reacting Golang? If you want performance today, you have to go there. But let's say you want to just, I'm going to scale to million users maybe in 2025, you can very, very well write Java, and then you download the latest version of Tomcat or Jetty, your code is ready to serve millions of people.
I think I would add a few more things from my end. I think I have shared across the feedback link. So if you have, Srinivas, can you meet for a second if it is fine? I think I'm getting an echo.
I could meet back. So okay, once you finished, I'll be staying here.
Sure. Yeah, sure. I was just trying to say, like, I have shared across the link of the feedback session. So in case if you have any feedback for the session, so you can write it down on the feedback link, except that we would upload the entire video of the entire session on YouTube. So you can even check that up. And I would like to thank Srinivas for the pretty amazing and insightful session, and even the audience for taking out time. If anyone have any more questions to add on, you can still add it up. Yeah, I think we can exit probably. I think no one have any question and stuff. Yeah.
Okay, I'm staying back. I think you will take a. Do I need to press exit or what?
No. I would do it.
Okay.
Yeah. Thanks once again, Srinivasan. Thanks everyone. Have a great evening ahead, everyone. Yeah.